Morning. So today we will study structure from motion. So let's briefly recap what we've studied so far. This slide is from lecture 7, the previous class, and the entire pipeline is about multiple geometry theory, and there are several stuff that we learned. So there can be two directions. The first one is assuming we have checkerboard with known 3D measurement, then we can perform camera calibration to get camera intrinsic and extrinsic. That is a lecture 4, this one. And then another input of our system is multiple images from video, or multiple images from diverse viewpoint. Anything is okay. Then we can use image matching algorithm. Representative algorithm is a SIFT, right? We can use SIFT to do the image matching to get match point from multiple images. And then if we do not have checkerboard, if we do not have 3D measurement, then we can use epipolar geometry to get essential fundamental metrics. That gives us, these matrices gives us camera information up to scale. So there's scale ambiguity. So if we have checkerboard with known 3D measurement, we can triangulate points from multiple images to a 3D space without any ambiguity. If we do not have checkerboard, if we do not have any known 3D measurement, then there is scale ambiguity, but we still can triangulate points from multiple images to 3D space with scale ambiguity. So that is what we learned so far. And today we will study a application, one of the most widely used algorithm in multiple geometry theory, structure from motion. The structure from motion is just the below part. If we do not have any checkerboard, if we do not have any measurement, then we still can triangulate. We can still lift the point to the 3D space. That is structure from motion. Structure is a 3D geometry. Structure, 3D geometry. Motion is, from a video. So getting 3D geometry and camera parameters. Motion means like a motion of camera. It is a motion of camera. Motion of camera. So if we have some images with diverse camera motions, then we can recover both 3D geometry and camera parameters at once, and that is called structure from motion. This is in one sentence, this is the goal of structure from motion, in short, SfM. And SfM, not a special thing, just a below part. Assuming we do not have, if we do not have any checkerboard, if we do not have any 3D measurement, then we can skip the above part. We can skip this part and just rely on the below part. That is just called structure from motion. So there is no very new stuff, but we would like to assemble every pieces that we learned so far to get to know what is the structure from motion. So starting from multiple images, usually images are from a single video. Let's say we took a video with our mobile phone without any 3D calibration. That's okay. Assuming we just take a video with our mobile phone, then we have, every frame becomes images, right? And then we can use image matching algorithm to get points from multiple images, and then we can use epipolar geometry, and then we can use triangulation to lift the points from points from video and essential fundamental matrices to the 3D space. And as I said, in structure from motion, we have scale ambiguity because we do not have any 3D measurement. So that is the reason why we rely on epipolar geometry, and we have scale ambiguity. That means we can't determine a single scale. But still, we can lift the points to 3D space, so that is good. It's a very practical algorithm. This is just called structure from motion. And so given many images, we'd like to figure out where they are all taken from. That is about camera extrinsic, right? This is camera extrinsic. And build a 3D model of the scene. 3D model is a little bit ambiguous, but let's say this is a 3D geometry of the scene. We can still recover 3D textures, so 3D geometry and texture. Okay. So just input is just many images. So this is very practical without any measurement, 3D measurement. We'd like to recover both camera extrinsic, intrinsic, 3D geometry, texture, all once at the same time. So that is structure from motion. This is just a very the brief result of the structure from motion. We can use images from internet, very uncalibrated images, or we can use a video. Anything is okay. Any multiple images is okay. And then we can lift the 3D geometry and texture to the 3D space. You can see this landmark, right? So this is structure from motion. Actually, structure from motion is very widely used. Phototourism is from SIGGRAPH 2006. We can use photo collections in the web to build a 3D geometry and texture of landmark, and then we can use such kind of recovered structure to do some interesting things. And these are all possible. These are already from 2009. It's about 15 years ago about. At that time, we already can get this kind of reasonable quality of 3D geometry and texture if we have enough number of images. So these are contents of today. We will study maybe up to here today. Ambiguities and structure from motion, affine structure from motion. But there are two kinds of structure from motion: affine structure from motion, perspective structure from motion. Let's start with the ambiguities. So as I said, structure from motion, the goal is to recover 3D geometry, texture, camera parameters at the same time from multiple images. And let's recall, the calibration is, we are not going to do camera calibration because we assume we do not have access to a checkerboard. But just to recall, what is calibration? Given a set of 3D known and known 3D measurement, we'd like to compute camera parameter. That is a calibration. And triangulation is known camera parameter and projection of the same 3D point in two or more images. Compute the 3D coordinate of that point. If we can use checkerboard, then camera parameter might be very good. If we do not have checkerboard, then we can use epipolar geometry to get essential fundamental matrices which have scale ambiguity. But still, we can lift the point to the 3D space using triangulation. And let's see the mathematical formulation. So given m images of n fixed 3D points such that ignoring visibility. So we'd like to, that is the formulation. Very simple, just a, so the lower one is just a coordinate in image space. And so this is image space. And this is word space. And this is projection matrix. So there are m images. That means there are m cameras and n fixed 3D points. So in 3D, there are n points and there are m cameras, right? So our goal is getting the purple one is what we have, and the red ones are what we want to get. Camera projection matrix and 3D, word coordinates of points. That is what we want to get. The problem is estimate m projection matrices, Pi and n 3D points, xj, from the mn correspondences, xij. That is the mathematical formulation of structure from motion. So as you can see, there are, so here m equals to 3, right? M equals to 3, and n equals to 1, 2, 3, 4, 5, 6. So there are 3 cameras in this below example. And there are 6 3D points, right? As I said, we have scale ambiguity. This shows the scale ambiguity. As we do not have any 3D measurement, so if we scale the entire scene by some factor k, and at the same time scale the camera matrices by the factor of 1 divided by k, the projection of the scene point remains exactly the same. So this shows the scale ambiguity. Mathematically, this shows scale ambiguity. We scale entire scene. This is the entire scene, right? X is the entire scene. We can use some factor k to scale entire scene. And we can, at the same time, multiply p with 1 divided by k. That makes the same result, right? So there is scale ambiguity. So without a reference measurement, without any, for example, if without any checkerboard, without any 3D measurement, it is impossible to recover absolute scale of the scene. In general, if we transform the scene using and then we can generalize the scale ambiguity to transformation matrix. We can generalize this one. Generalize. We generalize scale ambiguity to any transformation matrix. In general, if we transform the scene using a transformation matrix Q and apply the inverse transformation here, right, to the camera matrices, then image observation do not change. The scale is just some special case, so just a specific example of this transformation matrix Q. We can apply any transform matrix Q, but still there is ambiguity. So structure from motion inherently has ambiguity because we do not have enough information, so we have ambiguity. So there can be, given only x, given only small x, there can be multiple solutions. Like, for example, so our goal is from small x, we'd like to get p and x, right? P and x can be answer, or 1 divided k, p, k, x can be also answer, or p, q inverse, qx. There are already 3 possible solutions in this structure from motion formulation. So there can be, infinitely many possible solutions, possible combinations of p and x that can explain small x. So there's an ambiguity in structure from motion. And let's see some examples of ambiguity. With no constraint on the camera calibration matrices or on the scene, we can reconstruct up to projective ambiguity. That makes sense, right? Because Q can be general full rank 4x4 matrix. That is, we learned this. Where is it? Yes. Let's see this one first. So we learned projective matrix in lecture 2. The H homography is just a arbitrarily homogeneous 3x3 matrix in 2D transformation. So that means in 3D space, Q can be full rank 4x4 matrix. It is projective transformation matrix, and that makes very ambiguity. There can be many possible solutions. P and X can be answer. P and X can be answer. P, Q inverse, QX can be also another answer. There can be many answers. So with no constraint on the camera calibration matrices, the P, if there is no constraint on camera calibration matrix or on the scene, then we can reconstruct up to projective ambiguity. This shows the projective ambiguity. Q is just a projective transformation matrix, right? So there can be many possible solutions up to projective ambiguity. This shows ambiguity of structure from motion. And this shows some example. Projective transformation, it does not preserve parallelism in the image space, right? So so the recovered 3D geometry could seem like this. This is not what we want, right? And affine ambiguity. We learned affine transformation matrix in lecture 2. Affine transform matrix. So the projective one, let's say projective is just the 4x4 matrix. 4x4 matrix. any numbers. But affine transform matrix, the below row vector should be 0, 0, 0, and the last one should be 1. So that we can reduce the ambiguity, right? We can reduce the ambiguity to up to affine transform matrix, but still there's ambiguity. So if we impose parallelism constraint, then we can get a reconstruction up to an affine ambiguity. This shows the example. And this shows the affine ambiguity. So there is a constraint. If there is no constraint at all, then our SfM algorithm has a projective ambiguity because of this Q, full rank 4x4 matrix. But if we affine transformation preserve the parallelism, right? So if we impose parallelism constraint, this is just our assumption. If we impose parallelism constraint, then we can reconstruct up to affine ambiguity. And this shows the result. Still not very good, but a little bit better than previous one. And similarity ambiguity, a reconstruction that obeys orthogonality constraint on camera parameters and or scene. So that if we give stronger constraint, a orthogonality, then we can use similarity matrix, right? Similarity matrix is just a combination of scale, rotation, and translation. Then our structure from motion algorithm can reconstruct parameters and 3D scene up to similarity ambiguity. So this just shows the example. I mean, if we give stronger constraint, then we can reduce the ambiguity. But inherently, we always have ambiguity. If we do not have any constraint, we have projective ambiguity. There is no constraint. If there is no constraint at all, then we have projective ambiguity. If we have parallelism constraint, then we have affine ambiguity. And then if we have orthogonality constraint, then we have similarity ambiguity. And these are just examples. The important thing is that our structure from motion algorithm always have ambiguity. So as I said, there are two kinds of structure from motion: affine structure from motion and perspective structure from motion. We will study both kinds of structure from motion. Affine structure from motion, from its name, we can see affine, right? So approximate camera as a parallel projection, valid when scene is far away without perspective effects. So, I mean, it used simpler camera model. The original camera model should be a pinhole camera model with perspective effects, right? We need to use perspective projection. But in this kind of affine structure from motion, because the structure from motion is too ambiguous, we'd like to give a little bit of strong constraint, so that we'd like to use affine transformation matrix. We'd like to do parallelism constraint to the structure from motion algorithm, so that we can reduce the ambiguity. That is the affine structure from motion. Approximate camera is a parallel projection. I mean, actually, this is not the not always true. I mean, the camera projection is not always parallel projection. This is just their assumption, and it is valid when scene is far away. If scene is very close, then this does not hold. But if scene is far away, then we can approximate camera as a parallel projections, and then we can use affine SfM. In general, we can use perspective SfM with standard camera pinhole model with perspective effects. So there are two kinds of structure from motion. This gives a stronger constraint, to reduce ambiguity. This is more realistic. So let's start with the affine structure from motion. Affine structure from motion. So structure from motion that estimate 3D structure and camera parameters from multiple 2D image correspondences. assuming affine projection, as I said. From its name, there are many affine, right? Affine projection, parallel projection, camera model. We do not use perspective projection. Perspective projection is the most realistic one, but as structure from motion suffers from ambiguity, we'd like to reduce the ambiguity, so that we'd like to use affine projection camera model instead of perspective projection camera model. So ignore perspective foreshortening. Parallel line remain parallel in the image. The reconstruction is unique only up to affine transform. We will study this later, but you need to. What I want to say is that affine structure from motion, it uses affine projection instead of perspective projection. As SfM suffer from ambiguity, we'd like to reduce the ambiguity. So it uses simpler camera model, affine projection. And let's recap the affine. I guess some of you guys forgot what is affine or what is perspective projection. So let's briefly recap what is affine and what is perspective projection. So this is from lecture 2. Affine is in 2D space. This is 2D space. Affine transformation matrix A is arbitrary 2x2 matrix. In homogeneous coordinate system, this transformation matrix should be 3x3. So the left upper part is arbitrary 2x2 matrix, and T is a translation, just as two-dimensional vector. And this is affine transformation matrix. And projective transformation matrix, that is the most realistic one. What we use in camera pinhole model, what we use in 3D to 2D projection. And so H is the arbitrarily homogeneous 3x3 matrix specified up to scale. So that here it has 6 degree freedom. The reason is that this is arbitrarily 2x2 matrix. So this is 4 and this is 2. So 4 plus 2 becomes 6 degree freedom. So in 2D space, we can compute degree freedom of affine transform matrix. A is arbitrary 2x2 matrix, so it has 4 degree freedom. Translation, it has 2 degree freedom, so that combining this one, we get 6 degree freedom. That is affine this is affine transformation matrix in 2D space. So what about projective transformation matrix? Another word is called homography, and here, so H is a 3x3 arbitrarily homogeneous 3x3 matrix specified up to scale. So we have 3x3 minus 1 because up to scale. So we have 8 degree freedom in 2D space. So the affine transform matrix, parallel line remain parallel under affine transformations. But projective transformation, parallel does not hold, right? For example, this line are parallel in the original space, but no longer parallel. And this makes the distortion, right? We've seen this distortion. Parallel lines in 3D space cannot be parallel in 2D space. This is what we can see when taking images, right? That is from perspective projection. 2 parallel lines in 3D space might not parallel in 2D space. That is because the camera pinhole model uses projective transformation. If we use affine transformation matrix, then parallel lines in 3D space is always parallel in 2D space. That is not the real one. It is simpler one. And this shows the summary of 3D transformation matrix. So affine, it has 12 degree freedom. The reason is that A, T, 0. So this one has 3x3, and this one is 3-dimensional. So that we have affine transform matrix, we have 12 degree freedom. And this one, it has just the arbitrary 4x4 matrix minus scale, because it's scale ambiguity, up to scale. So we have 15 degree freedom, right, in 3D space. And this is also from lecture 2, and we will use affine projective many times from now, so it's better be familiar with this kind of what is difference between affine and projective. And projective is the most realistic one. It is used in standard camera pinhole model, but structure from motion suffer from too many ambiguity, so we'd like to relax the ambiguity by approximating camera with the affine transformation matrix. That is affine SfM. Affine SfM here. Ignore perspective foreshortening. Perspective foreshortening means, parallel lines in 3D space. This is perspective foreshortening. Parallel lines into 3D space can no longer be parallel in 2D space because if we use perspective projection, but when we use affine perspective, but an affine parallel line is always parallel in 2D. It is not very realistic, but it has less degree freedom. So we'd like to use affine affine camera model in affine SfM to relax the ambiguity of structure from motion. And this shows projection matrix. So we've seen this projection matrix. Where is it? Projection here. We have P and X. X is the, as I said, 3D coordinates, 3D position is the world coordinate system. And P is the projection matrix. What is projection matrix? We've actually already learned projection matrix in lecture 2. Projection matrix is a multiplication of extrinsic and intrinsic matrices. Extrinsic is a rotation translation, right? Intrinsic is focal lengths, principal points. So that means if we use projection matrix, then we can convert world coordinate system to image coordinate system, right? You can ignore these details, but just the projection matrix is just the multiplication of extrinsic and intrinsic, so that we can just directly take world coordinate to transform it to image coordinates. Okay, then I hope you now familiar with projection matrix and affine and projective transformations. So what is, and the general affine projection is like if we'd like to project 3D pointer to this space, then we can use this projection matrix. And then as we are going to use affine projection, then our projection matrix looks like this. Originally, this 0, 0, 0, or the original stuff, originally, if we do not use affine projection, if we use just the original perspective projection, then 0, 0, 0 should be like a A31, A32, A33. But as we are going to use affine projection, then these three numbers are set to 0. That is affine projection. And in non-homogeneous coordinates, we can just decompose this into matrix multiplication and summation, right? Multiplication of affine transformation matrix and translation. So this just shows a example of affine projection. So given m images of n fixed 3D points such that xij is a multiplication of xi, xj plus ti. So ai and ti are defined for each camera, right? Because they are from projection matrix. Projection matrix is a multiplication of extrinsic and intrinsic, so that is defined for each camera. So that assuming we have m images, that means we have m cameras and n fixed point, so the xj. Problem is to use the mn correspondences, xij, to estimate m projection matrices, ai, and translation vectors, ti, and n points, xj. The reconstruction is defined up to arbitrary affine transformation q, as I said. Structure from motion suffer from ambiguity, But in affine SfM, we'd like to use affine camera model, affine projection camera model, so that our SfM has ambiguity up to affine transformation. And 12-degree freedom, we've already learned this, right? 12-degree freedom, where is it? 12-degree freedom. In 3D space, affine transformation has 12-degree freedom. So 12 is from this number. Yes, so the Q has a 12-degree freedom. And this shows just the ambiguous case. I mean, if we can, this is the original P, this is original X, but then we can P Q inverse QX, the same thing, right? PX is P Q inverse QX, right? And how many knowns and unknowns for M images and N points? We know 2Mn, right? Mn. We have Mn correspondences, and it gives us X and Y positions. So we know 2Mn, right? What we know is 2Mn. And 8M plus 3N are unknown. Where they come from? 8M. So, I mean, this is 8M. No, camera matrix, the projection matrix. Our camera, where is it? Yes, and then this is 2, and this is 2 by 3. So that we have 8 unknown thing in camera projection matrix. And then 3n is we have n 3D points and x, y, z coordinate. So we have 3n. So this is from camera, this is from P, this is from X. This is from small x. We know small x, that gives us 2Mn. And in camera projection matrix, we do not know 8M. And in 3D points, 3D coordinate, we do not know 3n. Right? So to be able to solve this problem, we must have, I mean, what we know should be, we need to know more than what we do not know, right? So this is what we know, 2Mn. And 8M plus 3N is what we do not know, and we need to subtract 12 because our structure from motion has affine transformation ambiguity, which have 12-degree freedom. So we'd like to subtract 12, so that this is our kind of condition to be able to solve this problem. So for example, let's say we have two views. Two view means we have m equals to 2. Then we can just plug in. Then 4n 16. So this gives us n should be equal or larger than 4. So if we have two views, then we need 4-point correspondences in theory, right? What we know should be larger than what we do not know, and we need to subtract affine transformation degree freedom because our algorithm has up to affine transformation ambiguity. And then if we have two views, that means m equals to 2. Then we can just plug in m equals to 2. Then 4n should be equal larger than this one, 16 plus 3n minus 12. So that gives us n should be equal larger than 4. So we need at least 4-point correspondences to recover camera parameter, to do structure from motion, to recover camera parameter and 30 point at once. This is condition to solve the problem. So this is a little bit complicated, so that you need to be familiar with this kind of stuff from lecture 2. What is affine transformation? Where did 6 number come from? Projective projection, and where does 8 come from? And what is difference between affine and projective? And in 3D case, the degree of freedom becomes 12 and 15. and what is projection matrix. And then based on some simple linear algebra, then I guess you can make it. Okay, any question? Not anything is unclear? It's okay? So these are just theory, and if you just implement system, you do not have to implement all this mathematical equation in your system. You do not have to do that. It's just a theory. And if you, for example, if you want to run some structure from motion, then you can use pre-built algorithm or there are actually already many off-the-shelf structure from motion libraries, so that you can just simply use them. But these are just theory. But the important thing is that, you need to be familiar with what is ambiguity. Well, we learn lots of algorithms, right? And each algorithm has pros and cons. So you need to select what is the proper algorithm in your specific cases, and you need to be careful what is the ambiguity of your system. So that is the reason why we learn this kind of stuff. There is always ambiguity, and how can we handle ambiguity? Which kind of ambiguity do algorithm have? And what is the pros and cons of each algorithm? And let's see the affine structure, affine SfM, more detail. So first, we center data by subtracting the centroid of the image point in each view. It's just a translation normalization. And after centering each normalized 2D points, x, I, j hat is related to the 3D point by this one, just the translation normalization. And we can get rid of the need to center the 3D data and translation ambiguity by defining the origin of the world coordinate system as the centroid of the 3D points. Now, these are just the mathematical convenience, not very, this is not a very big thing, just for mathematical convenience. And then let's construct a matrix D. Let's create 2m by n data, measurement matrix. Measurement matrix means all things are what we know. So cameras, 2m means there are m cameras and we have x, y. So that we have 2m elements, 2m row, and we have n points, right? So that this is 2m by n matrix. And we can decompose this matrix to camera and points, right? Camera is 2m by 3, and point is 3 by n. So that from this D is what we know, right? And M and S are what we do not know and what we want to get, right? So from matrix D, how can we recover camera parameter matrix M and points S? That is the goal of affine SfM, right? So I guess if you take linear algebra, I guess you are a little bit familiar with this figure. So D is a 2m by n matrix. M is 2m by 3 matrix, and this 3 by 2, just n matrix. We always use SVD, right? Now, again, we use SVD. So that means in classic computer vision, SVD was very popular. Although these days SVD is not very widely used, but very powerful tool to solve this linear system. This is just an example of SVD, right? We can perform SVD to the D, that we can decompose this matrix D to three things, and then we keep top 3 singular values. This is the closest approximation of D, right? We use top 3 singular values of D with rank 3 matrix in terms of Frobenius norm. And so D can be decomposed to these 3 matrices, approximated with this multiplication of these 3 matrices. And now we have 3, right? The reason why we like to use top 3 is that we are interested in specific shape, specific dimension of matrix. M should be 2m by 3 and S should be 3 by n. That is the reason why we keep top 3 singular values to approximate matrix D with top 3 singular values. So that our original goal is getting M and S, right? From D, it is known. What we want to get is M and S. So one solution, we already have solution, right? After SVD, we have already solution. One solution is like we can use U3, and then we can just make a square root to this sigma matrix. So this can be, this can be one solution. Just the multiplication of U3 and square root sigma 3, and S can be sigma 3 square root and V3 transpose. This can be one solution. We already have solution after performing SVD. But maybe you can get this. There can be many solutions. This is just a one possible solution, but because of the ambiguity. So so as I said, we have, this is just a one solution. U3 square root sigma 3 trans, and then S is a sigma 3 square root and V3 transpose. This is one possible solution. But there are actually many possible solutions because we have ambiguity. If we multiply this M and Q inverse S, then there can be many solutions. And square root is just one of possible solutions. We can use square root or anything to make to get D. And the only way to eliminate ambiguity is assumption, some prior, because we do not have observations. We do not have enough observation. In Bayesian rule, posterior. It's just a multiplication of likelihood and prior. Likelihood is observation. We do not have observation. Then the only way to get good model is using prior, based on Bayesian rule. If we do not have observation, then the only way to get good model is using prior. Prior is assumption, right? Without observation, based on human knowledge, we'd like to do some constraint or assumption. So the only way to eliminate ambiguity is using prior. That means assume certain special structure of the projection matrix. And then if we use affine transform matrix, then we can a little bit relieve the ambiguity, right? Assume certain condition about 3D structure. There can be two ways. We assume something in camera projection matrix. We assume something in 3D structure. The perspective projection matrix, it has too many degree of freedom. So that is the reason why in affine SfM we can give strong constraint to decrease the degree of freedom. That is the one way to eliminate ambiguity. The other way to eliminate ambiguity is assuming certain condition about the 3D structure, 3D geometry. Let's say we know these points are from some classroom. Then maybe most of the classroom have a shape of cubic, right? Cubic or, right? This kind, there are orthogonality. So we can use such kind of assumptions or prior knowledge of the 3D structure to give some certain condition. Or let's say we know this 3D structure is from mobile phone or there's some bottle, then we have some kind of prior knowledge of the mobile phone or bottle, so that we can use such kind of certain assumption of the structure. That is the other way to eliminate ambiguity. But the only way, as I said, the only way to eliminate ambiguity without additional observation is just using prior based on Bayesian rule. Very clear. If we do not have more observation, like if we have observation to the checkerboard, then we do not have scale ambiguity. Then we can make our algorithm better. But if we do not have any more observation, then the only way to eliminate ambiguity is always using prior. This is not only special case of SfM. Entire algorithm in computer vision, if we do not have observation, then the only way to make the model better is using prior. Anyway, so the only way to eliminate ambiguity in structure from motion is using prior, like assuming something in camera projection matrix, assuming something in 3D structure. In both ways, we can eliminate ambiguity. Then we can estimate Q to give the camera matrices in M desirable properties like orthographic projection. We will not see details. How can we estimate Q? How can we give some constraint to matrix M? That is a little bit complicated. We will not see details though, but the important thing is that you need to understand why we have this kind of ambiguity in SfM, and how can we eliminate ambiguity? What is the typical way to eliminate ambiguity? What people did? And one way is using orthographic projection or affine projection to the camera parameter. That is the first way, right? First way, this one, first way. First way to eliminate ambiguity, assuming something in projection matrix. That is affine SfM. Because of this, based on this SVD, we now get to know why this kind of ambiguity happens. And then affine SfM tries to relieve this ambiguity by assuming affine projection matrix instead of perspective projection matrix. As I said, the other way is assuming something in 3D structure. As I said, if we know where these images are taken from, if the images are taken from classroom, then we can use such kind of cubic structure to give some constraint to the matrix S here, so that we can relieve ambiguity of our SfM. And dealing with missing data. So far we have assumed that all points are visible in all views. And in reality, that doesn't happen. In reality, the measurement matrix typically looks something like this. So this kind of problem are called low-rank matrix completion problem, solved with convex, non-convex optimization. You do not have to memorize this stuff, but you need to be, the reason why I introduced this one is that the previous ones are assuming very ideal case. In reality, there is always visible and non-visible, and so that this is just a theory, and but in real implementation algorithm, people tries to consider this kind of missing data, invisible points, wrong matched result, to make the algorithm robust. It's okay? Good? Any question? So summarizing affine SfM. So based on this mathematical decomposition, we have ambiguity. This kind of Q affine, projection matrix. Q can make the multiple solutions. So then we'd like to use affine projection instead of perspective projection to give some constraint to the camera matrix M. That is the motivation of affine SfM. What we do in SfM, affine SfM, instead of using perspective projection matrix, we can use affine projection matrix. And the second kind of SfM is projective SfM. So far we've learned affine SfM, but from its name, you can know that from now on we do not no longer use affine transformation matrix. We now use projective SfM, projective projection matrix. And this shows the comparison between affine and perspective. So as I said, now I hope you are now can understand what I said here. Stronger constraint to the reduced ambiguity. As we have ambiguity, we'd like to use affine camera model, affine projection matrix when in camera model instead of perspective projection. That is affine SfM to relieve the ambiguity. But in perspective SfM, we now use standard camera pinhole model with perspective effects because affine SfM, it is valid only when scene is far away. But perspective SfM, it can be used for any cases, the most realistic one, because there's less assumption. So let's go to projective SfM, and let's recap the SfM. It is the same. Goal is the same, just from MN correspondences. Just 2D match 2D points, M images of n fixed 3D points such that Xij, Pi, Xj. The problem is to estimate M projection matrices, Pi, and n 3D points, Xj, from Mn correspondences, Xij. So the goal is exactly the same, but the difference is that in affine SfM, we assume this Pi belongs to affine transformation matrix, but now Pi is not. Pi belongs to perspective projection matrix. So the problem is exactly the same. Given is exactly the same, but these one are different. With no calibration information, camera and points can only be recovered up to 4x4 projective transformation Q. Here we use projective because we are not interested in projective SfM, not affine. The same thing, 2Mn is from, we have Mn correspondences, right? XY, so we have 2Mn. 11 is from, the P is 3x4 matrix, and we have up to scale, so that becomes 11. 11 is come from here. And 3n, we have n 3D point, xyz, so we have 3n. And 15 is 4x4 perspective, projective transformation has 15 degree of freedom because of the scale. So we have 15, we subtract 15. The logic is exactly the same. The only difference is that we now use projective camera model instead of affine camera model. That is the only difference in formulation. So let's say we have two cameras, that means m equals to 2. Then we can just plug in 4n should be equal larger than 22, 3n, 15. So n should be equal larger than 7. So in projective structure from motion, affine, we needed only 4 points, right? Because we use stronger prior, then we can use less observation. But in projective, we use less prior, then we need more observation. So that is the reason why we need more points. We need 7 points, more than 4 points in affine. And in perspective SfM, there are two kinds of SfM, unfortunately. So a little bit complicated. Affine SfM and perspective SfM, and they are global. White. Global and incremental. So in perspective SfM, there are global SfM, incremental SfM. So we just they're no longer SfM. So these are just the 3 SfM we will learn in SfM. Global SfM, incremental SfM, both belongs to perspective SfM. So these are, as I said, the difference is that affine SfM uses affine camera model, perspective SfM uses perspective projection camera model. Stronger constraint, less observation, less constraint, more observation. This is the difference between affine and perspective SfM. In perspective SfM, there are global and incremental SfM. Global SfM, from its name, it try to use some kind of global stuff. Use all pairwise relative poses together and solve the entire camera graph at once. That is global SFM. So the important thing is that all pairwise. So I mean, let's say we take a video from with our mobile phone, then we have frames. We have multiple frames. Then there can be relative pose between frames. We use all the relative pose of all frames, all pairwise relative pose together, and solve the entire camera graph at once. That is the global SFM. And incremental SFM is a little bit different from global SFM. Start from a small set of images, and then cameras, and add cameras one by one, expand the reconstruction gradually. So I mean, this one, like if we have n images, we have m images. It uses all the m images at once to recover camera parameters and 3D structure. That is the global SFM. Incremental SFM, if we take a video, then we have some frames of initial part, like this is just a time step. We can use small set of frames at the start of the video. Then we have some images, some 3D points and 3D camera parameters, and then we add frames, we gradually add frames to get camera parameters and 3D geometry of the following frames. That is the incremental SFM. So there are two kinds of SFM in perspective SFM. And this is global structure from motion. As I said, it tries to use all pairwise from the video. So feature detection is just a SIFT. We learned SIFT, right, in image matching. SIFT, and then we can match features between each pair of images. Let's say we assume now we have some matched result, and then we can, of course, do the epipolar geometry to get fundamental essential metrics, and then do ransack to refine matching, anything that we can do. We've learned this all this stuff, right? And link up pairwise matches to form connected components of matched across several images. There's just a image matching, right? And this shows global SFM. A little bit complicated. Given n images, there are, so let's say we have n images, then there are n combination 2 pairs that we can select 2 images from n images, right? Many of these pairs will have no overlaps in views, and our fundamental essential metrics between the m cannot be reliably estimated using ransack. So, I mean, that's true, right? If we take a video, then if we take a video, and this is time step, frames of this early part and last part might not have any overlap, right? So consider we have n0 pairs of images with fundamental matrix estimated. And for each n0 pairs of images, decompose essential matrix into relative rotation translation between 2 cameras, Rij and Tij. That is the epipolar geometry, right? I mean, if we assume as we already have matched result, then we can perform epipolar geometry, and then for each n0 pairs, we can get essential matrix. Essential matrix is like only extrinsic, right? It does not have intrinsic. We can decompose it to relative rotation translation between 2 cameras, right? That is just image matching and epipolar geometry that we learned. And the goal is getting global rotation and translation cameras given pairwise measurement. So, I mean, in epipolar geometry, what we get is just a relative rotation translation. So, let's see this image. No, this one. So, these are what we get from epipolar geometry. The relative rotation translation between frames, between images. Right? But what we want is a global rotation translation, assuming there is a world coordinate system. This is world coordinate system. We'd like to get camera rotation and translation in world coordinate system, not relative stuff between frames. So how can we recover this? that is the global structure from motion. That is what global structure from motion is doing. Can we solve for global world coordinate rotation translation of the camera given pairwise measurement? So given Rij and Tij for n0 pairs, find Rk and Tk for n cameras. So Rij and Tij means so ith frame, jth frame. There we can get rotation and translation of between two cameras using epipolar geometry. That is Rij and Tij, right? We can do all these things epipolar geometry for every n0 pairs. But all we have is just a relative rotation translation between two frames. But what we want is global or world coordinate rotation translation, not relative rotation translation between frames. All we want is global world coordinate rotation translation, not this one, but R, K, T, K. Oh, sorry, here. Let's see T. So here we have two subscript, right? That means relative. Rotation between frame I, frame J. Translation between frame I, frame J. But here K means just a camera rotation, camera translation of kth frame relative to world coordinates, right? That is the relative between frame I and J. This is relative to world coordinate system. So this is what we get from epipolar geometry. And then global SfM. Can give us rotation translation of camera for each frame in world coordinate system. That is what global SfM is doing. And the way that we can get this is called rotation translation averaging. And once we have cameras, with rotation translation averaging, then we can get cameras, we can get rotation translation in world coordinate system, and then we can use these ones as an initialization, and then we can perform bundle adjustment to refine 3D geometry and camera parameters better. We've learned bundle adjustment, right? Bundle adjustment is like from initial camera parameter and initial 3D geometry, we can minimize reproduction error to refine camera parameter and 3D geometry. So from rotation translation averaging, we can get initial camera parameters. At first we have epipolar geometry to get rotation translation relative between each frame, and then we can use global SfM to recover camera rotation translation in world coordinate system using rotation translation averaging, and then now we can use bundle adjustment. Based on this initialization, we can use bundle adjustment to further refine the camera 3D geometry. So there are 3 steps, right? Sorry, it's very complicated. Epipolar, Rij, Tij. Epipolar, Rij, Tij, and global SfM rot trans averaging. That gives us Rk, Tk, and then bundle adjustment. Better rotation translation. So we have multiple images, then we have epipolar geometry to get rotation translation between each frame. And then we can use global SfM rotation translation averaging to get rotation translation in world coordinate system, not relative between frames. And then we can further refine them using bundle adjustment. So they are not very detailed. We will not see details, but just rotation averaging is just let's say we have RJ and TJ N0 pairs, find RK, TK for N cameras, and input is many noisy relative rotation. That is what we get from epipolar geometry, right? Problem is that they are inconsistent. For example, if we multiply relative rotation between R12 and R23, then we can get R13, rotation between frame 1-2 and rotation between frame 2-3. If we multiply them together, then we can get rotation between frame 1-3. But unfortunately, because of many noisy relative rotation, this does not hold. I mean, in theory, this should be hold, but because of the many noisy and wrong estimation, this does not hold. This is the problem. And our goal is find global rotation Ri that better satisfy all relation. And just so the averaging is a combining multiple noisy constraint into one consistent global solution in SO3. SO3 is like just the mathematical stuff, but we will not see detail. We will not see detail what averaging is exactly mean, but what we can say is that rotation averaging is just like to use all kind of relative rotation, and then considering all the relative rotation, we'd like to get best global rotation that best satisfy all relation. Translation is the same. We have relative translation between frames that we can, and they conflict due to scale measurement noise. So we estimate global camera position so that by averaging, just consider all the pairwise direction into one consistent global layout. We will not see detail, but this is the rotation translation averaging. So we have relative rotation between frames, but thanks to the rotation translation averaging, we can get this kind of rotation in world coordinate system. And translation is the same. And as I said, after getting rotation translation in world coordinate system, we can use bundle adjustment to further refine them. Right? Bundle adjustment. We can minimize the reproduction error to minimize. So here, initialize P projection matrix by solving global SfM, rotation translation averaging, and then we can further refine camera metric, projection matrix, and 3D geometry of the point. So the good point of global SfM is that less drift because solution is globally consistent and less sensitive to initialization, scales better for large internet photo collections, but I'm sensitive to noisy and relative pose estimation. Non-convex global optimization can be tricky. We'll see incremental next time. Anything you are unclear? Any question? Okay. Okay, let's check the attendance and finish today. Okay, let's finish. Thank you.